Alright, let's take a look at chapters 4, 5, and 6 and step back and take a more broad view of this, a little comprehensive view. I'm going to launch down here on the course content page down at the bottom a folder that says chapter 4, 5, and 6, a broad view. Okay? And we'll open that up, and it wants me to download the file and open it up. So there it is. Let's start the slideshow. What we want to bring together in chapter 4, 5, and 6 are the concepts that we talked about with Newton's laws. The first law, an object in motion at constant speed continues in that motion unless acted upon by a force. Second law, which relates then what is the force if there is a change in speed, Newton's second law, F equals ma. And then the third law, which relates what happens when there are interactions between objects, the concept of for every force there's an equal and opposite reaction. And then we went on to look at the concept of work and energy, approaching all these problems from that perspective, which was a scalar perspective instead of a vector perspective. And then finally in chapter 6 we take a look at momentum and the conservation principle associated with momentum and its relationship actually to Newton's second law, F equals ma. So in the Newtonian approach, we really were just simply talking about why things happen because of influences, which are the forces, and we had to look at what types of forces are we talking about. So that allowed us to bring into play the concept of weight as the force of gravity on a object. Friction, right, which was the interaction of surfaces in contact, and that was given by the coefficient of friction times the normal force. We looked at the expression of a force that would be applied if a spring were acting on an object, and we called that Hooke's law, which was minus kx. So we have a number of different expressions for forces if in fact the forces weren't stated already. Sometimes the forces are stated that there's a string pulling with a certain tension, or someone's pushing at an angle with a certain size force in newtons. So clearly that's something that would already be given. Other situations, we had to deal with vectors, such that we might have multiple forces acting on an object, and you had to break those force vectors down into their components and resolve them into a single force vector, because our ultimate goal is to try to understand, in terms of our coordinate system, x and y, well, how are things moving? What is the acceleration, resulting acceleration in each direction? Acceleration in the x direction, acceleration in the y direction, as a result of the various forces that are acting on the object. So that's really what brought in, I think, the complication in Newton's second law, was just all of the little individual descriptions that came into play. But the idea, the general idea of F equals ma is very simple, isn't it? That identify what forces are present, and that means, because forces are vectors, identify their direction and size, and then once you know what that is, you can then express then, well, what is the subsequent motion due to that force acting on that mass? So it's pretty straightforward when you think about it. Okay. Well, of course, the only complication there was we had to deal with vectors, and that brought into play the idea that we had to look at sines and cosines and use the Pythagorean theorem. Now, the next approach we took was then to say, okay, well, is there a way to look at this such that we don't have to deal with the vector nature of forces? And there's this way which deals with the concept of work and energy. So recall that we developed, get my colors up here, We developed the idea of work by examining what it means when an object is experiencing a force, and that force is continuously applied to that object as it is displaced across some distance d. And of course the object has mass, and if we thought about it, realizing that, let's say the object starts with a zero velocity, and you know from your experience that if you apply a force to a mass, push it continuously over distance d, its velocity is going to change from something to something else. Here, from zero to something non-zero. So you, as the external agent, have exerted this force, and we defined then that you did work given by the product of the force, then the distance. Remember, the cosine is there to account for the fact that what if the force vector were not pointing along the direction d, but were up at some angle, theta, to that direction? Then we only want to know how much of that green force vector is parallel to d, and so that's what F cosine theta is, the amount of the force parallel to the displacement d, because that's the only component of the force that is effective, doing work in moving the object to the right in this case. And then we saw that then, as a result of that motion, that the object mass m starting at zero ends up at some final velocity, meant that it had something that we defined as kinetic energy, which changed in the process of going from one point to another point. This combination 1/2 mv squared took on a different value. Okay, that was for motion along a level surface. We then looked at what does it mean to move up or down. Okay, undergo a vertical displacement for our mass m and take it up from one point to another. In the process, we're working against. In other words, gravity is pulling down with a weight mg. So that means you, the person lifting, have to apply an equal force of mg upward. So once again, you are exerting the force, so you're doing work, and you're displacing over a distance d. Of course, in the vertical direction, we would call that y. So mg times y defines for us the concept of gravitational potential energy. And that's called energy of position because that energy is present as a result of the position of the object in the gravitational field as characterized by the acceleration g. In a similar fashion, you think about a spring. If I can draw a spring here, the spring being compressed because an object is sitting on that spring. Let's put a big black ball on that spring there. That spring will compress, therefore the object, the compression of the spring, by the way, due to the weight of the object, the compression of the spring is also a change in position, a change in the length of the spring. Therefore, it's a potential energy also related to position, in this case, the overall length of the spring. So in both cases, we can't define one single term as potential energy like we did up here with kinetic energy. There was only one expression for that. Down here, the expression for potential energy depends on, well, what is the particular force that's responsible for this potential energy? Okay? Well, that made it a little complicated because we have multiple formulas. Then we found that if we examined the motion of an object and looked at what its kinetic energy was at one point and at another point, remember, like the idea of a car going down a hill and coming back up the other side of the hill. And ask the question, do we know the total mechanical energy at the first point? And total mechanical energy, E, is the sum of K and U, isn't it? Okay. And if we know the total mechanical energy at one point, because we know what K is, we know what U is, then we ask the question, do we know it at this other point? Say it's going over a smaller hill, down into a valley, and back up a higher hill. So do we know the kinetic and potential energy at the start, and say at the end at the top of this other hill? And if the answer is yes, we know the kinetic and potential energy, then either that total energy in both positions is equal, because there's no mechanism for losing energy, such as due to friction, or it's not equal, because in the process of going from point A up to point B, we had to overcome some friction, and therefore we lost energy. So the work energy theorem is just simply saying, look at the kinetic energy and potential energy at the two places, subtract them, okay, the kinetic energy beginning and ending, and potential energy beginning and ending, and then ask yourselves, is the sum of those differences equal to 0? If it's not, then what that means is that there was some external force, and generally in our case it's friction, but that external force has eaten away at some of the energy you had, and so it's not all available to be reflected in kinetic and potential energy of your system. We'll look at a problem in Chapter 5 that deals with that. Finally, the Chapter 6 deals with the concept of momentum, which we saw was just simply the rate of change of the product mass times velocity, and that was equal to force. So the only reason that the product mass times velocity was changing was because something external to the mass was acting on it. And we defined the combination mv as momentum, and that in collisions, objects conserve momentum because there's no external forces. If object A hits object B, there's nothing outside of that acting. It's just internal, one acting on the other. So every collision must conserve momentum, because in the equation force equals delta P over delta T, there is no force. The change in momentum over time is equal to 0, and so momentum is conserved. So we'll look at a problem in Chapter 6 as we move forward here. So let me open up another window and get into some mastering physics. All right, we're here in Chapter 4-2 in Mastering Physics, and decide to look at the problem titled Velocity of a Roller Coaster Ranking Task. You'll notice down here on the picture referred to, showing a roller coaster at the top of a circular bump. Okay, and we are told that 6 roller coaster carts pass over the same semicircular bump. That means then the radius is the same. It's the same bump, so same radius. Okay, and the mass of the cart and passenger, the total mass here, is going to be changing. We have 6 different masses listed over here on the right, and there's also a normal force, which is the ground pushing up on the cart, is different for each of the circumstances. And the reason it's different is these carts will be moving at different speeds. So how do we want to approach this? Clearly you could say this is in Chapter 4, so this is a force, this is Newtonian mechanics type problem. And that's true. That's probably a good guide. If you know what chapter you're in, you know what kind of concepts we want to use for the problem. So let's approach this from the standpoint that it is Newtonian mechanics. Now, why is this circular path here important? Why are we being told it's following this semicircular bump? And what do we know about Newton's law as it deals with things that go in circles? Well, let's get the marker up here, and what we know is that anytime an object is going in a circle, Newton's Newton's law becomes mv squared over r. Okay, so the fact that you see a circular motion, you can immediately write down the product mv squared over r is the right-hand side of the cause and effect relationship. Now, as always, the left-hand side is, well, what are the forces acting on the mass? And immediately we can see, if we look at our picture, we've got the weight acting downward and the normal force acting upward. Okay, it's nice. Normal force is stated already, and we know how to calculate the weight from mg. Okay, so we've actually got the left-hand side of our second law here for circular motion. And remember that this form of the law is expressing the force that is acting toward the center of the circle. So if I were to write this in the form of F equals mv squared over r and put in to this equation the two forces, I would actually write it in the form, put it down here on the right hand corner, mg, because that's the force toward the center of the circle, minus n, which is the force away from the center of the circle, so that's where the negative sign. So I'm using toward the center of the circle as my positive direction. And of course, those are the forces that are causing the motion to be circular. So mv squared over r is the right-hand side. So we can rearrange that in any way. Now if we look at the problem, now it says rank the speeds of the different carts as each passes over the top of the bump. Rank the speeds. Okay, so that means we need an expression for v, the speeds. And we're getting that expression from Newton's second law for circular motion. So that's what we've got down here. Let's rearrange this. Okay, I'm going to divide by m, and I'm going to multiply by r. Okay, so that gives me gr minus nr over m. And that's v squared. Okay. Now, I assume that if v squared is the biggest, v squared will have the biggest v. That sort of makes sense, doesn't it? But if you look at those two terms, g is a constant and r is a constant, because we're told it's the same circle for each cart. So r is the radius of the circle. So gr is a constant. Maybe it'd be easier. Let's factor out the r. I'm going to put the r over here, and then I'm going to write parentheses g minus n over m. Okay, let me get a new color up here. All right, now we know what g is. G is 9.8. So this expression inside here, g minus n over m, well, n over m is simply the two things that are changing, aren't they? Here we have n. Let's take the first n is 300, and the m is 300, right? So the ratio n over m for the first choice up here is 1, isn't it? So this is 9.8 minus 1. Okay. 9.8 minus 1. So that's 8.8. All right. Now how does that compare to, let's pick another one. How about the second one? What if we pick the second one? N is 400 and m is 100. So the ratio n over m is 4. Well, g, 9.8 minus 4 is 5.8. So clearly that's smaller. So that means the velocity is going to be smaller for this one, 400 over 100, than it was for the 300 over 300. So you see that now? So really what we wanted, we had to find an expression. We started with our Newton's second law. We identified our forces, okay? we put them into our expression and solve an equation to find something that would tell us how the velocity is related to the quantities in this problem that are changing. And the quantities in the problem that are changing are the normal force and the mass. So go through each of those ratios of the normal force and the mass, plug them into this equation, and see which ones give you the largest quantity inside this parentheses. All right? It's not just the ratio n over m, it's g minus n over m that's important. All right. Okay, I hope that helps. Now let's go on to the next one. I'm going to pause, and we'll come back up and take a look at a problem in Chapter 5. All right, this is the problem in Chapter 5 titled, Where's the Energy? Now this is an interesting problem because it brings into play the conservation of energy principles, where we look at kinetic energy as well as potential energy, and as well as the concept of friction. So let's start with the picture here. Okay. We are told that the block in this picture is we'll consider the following situation. A block of mass m slides at a speed v along a horizontal smooth table. So smooth, the word smooth is used to indicate no friction. It slides down a smooth ramp. Again, no friction. And then slides along a rough floor. Rough meaning there's friction. Okay? Those are what those words mean. All right. Now, even before you start looking at the different parts of this problem, and knowing it's in Chapter 5, and the question is, where's the energy, you should start thinking about what kind of energy are we dealing with at each of the different points along the path of this box. Up here at the top, we have, it has velocity, so we know it has kinetic energy, 1/2 mv squared. And this problem is all symbolic, so there aren't really any numbers. So you want to jot down these various terms. Okay, so we have kinetic energy up here at the top. And also, since we are going from a higher position ultimately down to a lower position, we have some potential energy due to the fact that the box is at the top of a table whose height is given by h. And that's in the problem as well. Okay, so we know we have potential energy, mgh. All right. So that's the total mechanical energy of the box on the table. Now we know as it slides down the ramp, its potential energy, I don't know, if we'll call this 0, I guess, we'll call it the original, then we'll refer to the position here as 1, and this position down here at the bottom is 2. So in position 1, going from position 1 down to the bottom of the ramp, our potential energy is decreasing, isn't it? Because h is going from original value down to 0. Okay? Since there is no friction acting on it on this ramp, there's no way energy can be eaten up in the form of heat and so forth. Therefore, the potential energy that is lost in decreasing the height is gained in the form of kinetic energy. So at the bottom of the ramp, we're going to be going faster. Okay. Then, so at the bottom of the ramp, right down here at the bottom, all we have left is kinetic, because we're on the ground. But we haven't yet started sliding across to our final position. Ooh, that was a very bad 1/2 mv squared. Okay. So that's that right here at the bottom of the ramp. We might call that V sub b, right? Okay. And we can find out what V sub b is because the total energy at the top, which is K0 plus U0, has to equal the total energy at the bottom, which is K plus U, and U is 0. So all of that energy at the top gets converted into kinetic energy at the bottom. All right. Then we're told that the box slides across a rough floor. Let's make that a green path. So the green path slides across a rough floor and comes to a rest. That means if it comes to a rest at the end here, notice my green kinetic energy is 2, okay, or final. There's no kinetic energy at the end. How much potential energy is there? There's no potential energy at the end. So therefore, there's no mechanical energy remaining. E equals 0. Did we conserve mechanical energy? No, we didn't, did we? Because we started out with some. We don't know what it, if we had numbers, we could find a number, but we know it's 1/2 mv squared plus mgh. We started out with some, we ended up with none. So what does that mean when your total energy at the beginning, E0, and your total energy at the end are not equal? Well, that means that some external work was done on this object, non-conservative force acting, in this case friction, to dissipate that energy. And so the work energy theorem says that the work that was done, and in this case the work is done only on the bottom section here where the green path where there's friction acting, work was done to essentially eat up all of that energy that you had. Okay? But all you need to do in this type of a situation is write out the total mechanical energy at each position along the path, taking into account whether or not there is a non-conservative force acting on the object. And in this case, the only place there's a non-conservative force is on the horizontal rough floor. All right. Now I'm going to pause for a second and open up one more problem in Chapter 6, dealing with momentum. Okay, finally, momentum. This is one of the problems in Chapter 6 assignment 939, and it's showing us a graph of a force that is acting on a 270-gram ball that's dropped from 2.5 meters, bounces off the floor, and rebounds to a height of 2 meters. And the figure shows the impulse received from the floor. Okay, think about that just for a second. What that means is that when the ball first contacts the floor, there's a normal force. And as that normal force acts on the ball, over time, as the ball deforms as it strikes the floor and then comes back up, still in contact with the floor as it re-expands, there's a force acting over that duration of time. So we want to determine what is the size of that. Well, we have a picture of that force, but we don't know what the magnitude of that force is. We're not told what is F max right here. So we're looking for that value. Okay. Now this is obviously a collision between a 270-gram object and the Earth. So this is an impulse momentum problem. And in our derivation of the impulse momentum theorem, we rearranged Newton's second law, which was F equals ma, and placed the mass next to the velocity inside the delta v term, and wrote this as delta p over delta t. Okay? And then taking the delta t from the denominator, bringing it over next to the f, we have a relationship called the impulse momentum theorem. Okay. Now the graph depicts for us the force versus time. So the graph is actually showing us the relationship F delta T. And we can analyze that. If you think about the product of F, which is along the y-axis, and the product of T, which is along the x-axis, when you multiply vertical times a horizontal, you get an area. And so this is actually the area enclosed by this little triangular spike. So let's figure out what that is. I'm going to divide this into two pieces. This is actually two triangles, two equal triangles. Okay, I haven't drawn them very well, but so this is two triangles, and we know that the area of a triangle is 1/2 the base times the height, right? When we have two of those triangles, so the total area is twice 1/2 base times height, which is just simply base times height. Well, the base of this is 2.5 milliseconds, 0.0025 seconds, and the height is the unknown F max, which is what we're looking for. So that's how we get our unknown in this particular problem into the relationship. So the left-hand side of our equation up here, let's change color back to red, is going to be 0.0025 F max. Okay, so now we know the left-hand side. Now the right-hand side is the change in momentum. All right, well, the object is going from, let's pick it up here. The object is released from 2.5 meters. It strikes the floor and rebounds to 2 meters. So really what we want to know is how fast does the object strike the floor, and then how fast does the object leave the floor. Those are the two velocities that are going to go into mv minus mv0. v0 is how fast does the object strike the floor, and v is how fast the object leave the floor. Okay. Notice that v0 is a negative vector, so this is going to be minus a minus, so that's actually going to be a plus. So we have 0.27 is our mass in kilograms, and the difference in velocity between the downward and the upward. Well, if we go back to our kinematics expression, when we start with the velocity of 0 up here, and we fall a distance y under an acceleration of gravity g, we can use our v squared equals v0 squared plus 2ax formula to find out how fast we strike the ground falling a distance h, or in this case 2.5 meters, under the acceleration of gravity g. So we're going to strike the ground, v equals the square root of 2g times y. And then we're going to have, in order to go up from 0 back up 2 meters, because that's where we rebound to, we're going to have a velocity at the bottom equal to 2g times that 2 meters for it to rise back up to this position here where it has 0 velocity again. So that's what goes in. Use this formula to calculate the speeds that go in here, strike the ground, and strike the ground here and rebound here. And so again, we're using a general relationship, the impulse momentum theorem, with the definition of momentum. Remember, P equals mv. Try to find out what is the maximum force exerted on this object as a result of a collision with the Earth. Alright, I think that's it. If you have any questions, join the chat room or email me. Thank you.